Hello everyone. So in the previous class we have discussed about rectifiers. In today's class we are going to discuss about the photodiodes. So the photodiodes are two terminal device. As it is a diode, so obviously it is a two terminal device which is designated to respond to photon absorption, which are called as photodiodes. So photodiode produces current when junction is exposed to radiation. That is, some photodiodes are extremely high sensitivity and response speed. Since modern electronics often involves optical as well as electrical signals, photodiodes serve very important functions in electronic devices. Remember that it operates in a reverse biased condition. So photodiode is a two terminal device that is used to produce a current in the reverse biased junction whenever it is exposed to light. So its symbol, it is not shown in the slide, is normal diode symbol, but a radiation is exposed. Two arrow marks falling on the diode symbol is a symbol of a photodiode. Current and voltage is in an illuminated junction. So in the previous class we have discussed about the forward and reverse bias junctions. So recall the forward and reverse bias carrier concentration in a PN junction that resulted from the application of the bias. So forward bias increases the probability of diffusion across the junction exponentially. So that is, the equation I is equal to I naught into e to the power qv by kt minus 1. The total current is the diffusion current minus the absolute value of the generation current. At V equal to 0, the generation current and the diffusion current cancels. So total current I is equal to QA into dP by LP into Pn plus dN by Ln into Np into e to the power qv by kt minus 1. So that is equal to I naught into e to the power qv by kt minus 1. So here Ln and Lp are a length of the N and P, and Pn and Np are a equilibrium concentration of holes and electrons in N and P type material. So as you can see from the figure, so the figure shows the optical generation of a carrier in PN junction diode. So the absorption of light by the device. So you know the working of normal PN junction diode. So as you can see from the figure, the PN junction diode is reverse biased. So initially when the junction is not exposed, don't consider those arrow marks wherein the junction is not exposed. So initially when the junction is not exposed to any type of radiation, then only the minority current will flow through the device. As we know this, only the minority current, because of the minority charge carriers, flow through the device. That is, minority carriers in p side are electrons and minority charge carriers in n side are the holes. So due to these minority charge carriers, the current flow through the device whenever there is no exposure of the radiation. So the movement these minority carriers across the junction produces a small reverse current. So the movement of these minority charge carriers are going to produce a small reverse current. So it is negligible current which is almost equal to 0. So after a certain amount of time, the movement of minority carrier generation generates the depletion region across the junction. So that is shown. So this depletion region consists of neutral atoms, so that does not allow any further flow of electron or holes across the junction. So that is nothing but the depletion region. Now if we provide a radiation to the junction, that is, if the junction is illuminated with the light as shown in the figure, the arrow marks, so that is it is exposed to light. That photodiode consists of a window from through which the light is exposed on the surface of the junction. So when we provide the radiation to the junction, that is, if the junction is illuminated, then what happens? As the radiation falls on the surface of the junction temperature increases here. So as the radiation falls on this surface of the junction, the temperature of the junction increases. So the increase in the temperature results into separation of that electrons and holes that are present in the depletion region. So at the time of separation, they are going to separate here. Now as the temperature increases, they start separating. So at the time of separation, the holes present in this region gets attracted towards the negative potential of the battery. So as the battery is connected, P side is connected with the negative of the battery, N side is connected with the positive of the battery, because the photodiode works in a reverse biased condition. So the holes present in this region gets attracted towards the negative potential of the battery, and electrons attracted towards the positive potential of the battery. So due to this, the current starts flowing. So the flow of current takes place because of this increase in the temperature, because we have started exposing light on the surface of the junction. So due to this flow of current takes place, and with the increase in the radiation, the current in the device also increases. So as you increase the intensity of light, the current also increases. So the current in the device is, that's why the current in the device is directly proportional to the intensity of the light. So as the intensity of the light, the current in the device also increases. So the current is independent of voltage. So the applied voltage is nothing to do with here. So the whatever the current that is flowing now is totally, it is independent of the applied voltage. So this is the working principle of the photodiode. So as we are added the light to it, that is, we have exposed the photodiode with the light as shown in the figure, and added generation rate, that is GOP. So it is called as GOP, the added generation rate, participate in the current. So A into LP into GOP. So this is the extra hose generated on the N side. A into Ln into GOP. This is the extra electrons that are generated on the P side. And A into W into GOP are the extra carriers generated within the depletion region. The resulting current is due to the collision of the optically generated carriers. So that is given by IOP equal to Q into A into GOP into LP plus Ln plus W. So this figure shows the current IOP resulting from electron hole pair generation within a diffusion length of the junction on N side. So delta POP is equal to GOP into tau P, and IOP is equal to QALP into GOP. So GOP is nothing but it is a optical generation rate, and tau P is nothing but a recombination lifetime for holes. To find the total reverse current, we need to modify the diode equation that we have incorporated the new optical generation current. So the total current is nothing but I naught into e to the power qv by kt minus 1, that becomes ith into e to the power qv by kt minus 1 minus IOP. So IOP is the current directed from N to P. So I is equal to Q into Ni square A into dN by Ln into Na plus dP by Lp into Nd, bracket complete, into e to the power qv by kt minus 1 minus IOP. So this additional mechanism will change the output currents. So the IV curve will be lowered in an amount proportional to the generation rate. So as you can see from the figure, that is IV characteristics of illuminated junction. So when GOP is 0, this is a negligible current. As the intensity of the light increases in the device, as the PN junction is in the reverse bias condition, and as you are going to increase the radiation, as the intensity of the light increases, the reverse current within the device also increases. So that is the characteristics G1, G2 and G3. So as the intensity of the light increases, the current in the reverse direction also increases. So G3 is greater than G2 and G2 is greater than G1. So this is the IV characteristics of an illuminated junction in the photodiode. Now if we short circuit the device, that is V is equal to 0. If we short circuit the device, that is V equal to 0, then that I, the current equation I, that first term get cancelled. Q Ni square into A dN by Ln into Na plus dP by Lp into Nd into e to the power qv by kt minus 1. So this term get cancelled. Only remaining term is minus IOP. Now if we open circuit the device, that is if I is equal to 0 and open circuit voltage VOC is nothing but the open circuit voltage appears across the junction. So that VOC is equal to kt by q into Ln into IOP by ITH plus 1. So that is equal to kt by q into Ln into bracket Lp plus Ln plus W divided by Lp by tau p into Pn plus Ln by tau n into Np. So here Ln and Lp are nothing but the length in Lnp, and tau p and tau n are the recombination lifetime for holes. And Pn and Np are nothing but the equilibrium concentration of holes and electrons in N and P type material, and GOP is the generation of rate of generation. Now consider a symmetrical junction, that is Pn is equal to Np and tau p is equal to tau n. So this is a special case for symmetrical junction. Consider this symmetrical junction where the condition is Pn equal to Np and tau p is equal to tau n. Then we can rewrite the preceding equation in terms of the optical and thermal generation rate. That is VOC is approximately equal to kt by q into Ln GOP by GTH. For GOP is much greater than GTH, where GTH is nothing but it is equal to Pn by tau n. That is GTH is equilibrium thermal generation. So this is the band diagram of that one. That figure shows the effect of illumination on an open circuit voltage of a junction. The figure 1 shows the junction at equilibrium, and the second one shows the appearance, That is, B figure shows appearance of voltage VOC with illumination. So the appearance of a forward voltage across illuminated junction is known as a photovoltaic effect. That is, the photovoltaic effect is the generation of voltage and electric current across illuminated junction, that is, upon the exposure of the light. So in our semiconductor, the minority carriers concentration is increased by optical generation of electron hole pairs. So the lifetime tau n is decreased. This increases the ratio Pn by tau n. So VOC cannot increase indefinitely. So in fact, it cannot increase beyond the equilibrium contact potential, since the contact potential is the maximum forward bias that can appear across the junction. So the appearance of the forward voltage across an illuminated junction is known as photovoltaic effect. Now let us look at the IV responses again under illumination. So the figure shows the operation of an illuminated junction in the various quadrant of its IV characteristics. So in A and B, so A is nothing but it is forward biased. It's the first quadrant, as you can see from the figure. P is connected to the positive of the battery and N is connected to the negative of the battery. So it is a forward bias. And B figure, it is reverse biased. So first quadrant and third quadrant, figure A and B, in which the power is delivered to the device by the external circuit. So the power from this is going to be delivered to the device by the external circuit. But observe the figure number 3, that is figure C, in which PN junction is connected to the resistor. P and N are connected to the resistor. So here the device delivers powers to the load. So if power is extracted from the device, the fourth quadrant is used. On the other hand, in applications as photodetector, we usually reverse bias the junction and operate in the third quadrant. Thank you for watching the video.